Let's now continue considering inversions, and we will look at the image of a generic straight line. So we have so far considered special cases of straight lines, and generic means the most general, not a special case. So what are special cases we have considered? We considered straight lines passing from the origin, passing through the origin, like this. We considered images of such straight line. We considered images of the vertical straight lines and of horizontal straight lines. And now I would like to consider the image of a straight line, which here is horizontal straight line, and then I would like to consider the image of a straight line that does not have any special disposition, so just a line in a plane, the most general type. It will intersect both coordinate axes. It will go something like this. So there is a coordinate system, and there is a line going like this. It will intersect both real axis and imaginary axis, since it's not parallel to any of them, and it does not pass through the origin. So it passes through some point. For instance, this is point BI on the imaginary coordinate axis, and this is point A on the real coordinate axis. Let's look at the image of such a line. Altogether, when considering a straight line in the complex plane, how to write an equation of a straight line in the complex plane? I can tell you how to write. Suppose there is some line. It passes through points Z1 and Z2. That's all we need to know about the line. 2 points through which it passes. And suppose Z is some what we call current or floating point in this line. And let's try to write the equation of this line. So what is the condition of point Z being on this line? The condition is that vector connecting Z with any of these points, for instance this vector, Z minus Z2, will be collinear with the vector connecting these 2 points, Z1 and Z2. So Z minus Z2 is some real number multiplied by Z1 minus Z2, or Z2 minus Z2. In this case it will be Z2 minus Z1. Right? Or we can write, divide by Z2 minus Z1, Z minus Z2 over Z2 minus Z1 is some real number T, number that belongs to the set of real numbers. That would be a good enough equation of a straight line. Or of course we can rewrite it like this, that the imaginary part of Z minus Z2 divided by Z2 minus Z1 is equal to 0. And I think this is a convenient form of our equation 1, a convenient form of an equation of a straight line in the complex plane. What else should we do? What about imaginary part? We know that for any number, for instance number xi, which is equal to real part xi plus I imaginary part of xi, and xi conjugate will be real part of xi minus I imaginary part of psi. If you subtract one equality out of the other, we will receive that psi minus psi conjugate is 2i imaginary part psi. So imaginary part psi equals 1 over 2i psi minus psi conjugate. And this is a convenient presentation that we are going to use in our consideration. Now, we could have taken arbitrary numbers z1 and z2, but it is convenient since the line will intersect both real and imaginary axis anyway. Then we will take one point z2, for instance, on the real axis and z1 on the imaginary axis. Yeah? So our equation will be, I'm just rewriting equation number 1, imaginary part of z minus a over a minus ib equals to 0. That will be equation 1 for our case, or using the formula for the imaginary part, we will have z minus a divided by a minus ib minus z conjugate minus a conjugate, and a conjugate is a because it's a real number, divided by a, again it's conjugate, so it's the same a, plus ib equals to 0. The conjugation involved changing negative ib to positive ib. Right? So that's our equation. Let's simplify it as much as we can. We multiply by both denominators. So we will have z multiplied by a plus ib minus, now a multiplied by a and a multiplied by ib, minus a squared minus iab, then it will be, now I'm multiplying this part by number, so it will be minus z conjugate multiplied by a minus ib, and minus here and minus before a multiplied by a, so it will be plus a squared, and minus 3 minus, it will be minus iab, and the whole thing is equal to 0. That's our next equation. I will rewrite it again. I will first write a squared and negative a squared cancel each other. iab, negative iab plus z a plus ib minus z conjugate a minus ib equals to 0. That's our equation. That's our equation of the straight line. And now we'll apply the inversion w equals 1 over z, which of course implies that z is 1 over w, which we will substitute into this equation, and then we will get our equation in terms of w. We will see what image will be in the transformed plane, in the w plane, right? So it will be negative iab plus a plus ib divided by w minus a minus ib, instead of multiplying by z conjugate, divided by w conjugate, equals to 0. Now I will start erasing things because we need room. I hope everything is pretty clear here, so I will start erasing. let's multiply this equation. Let's multiply both sides of this equation by W conjugate. So we'll have negative I, sorry, there was IAB and another IAB, so it must be 2IAB. Negative 2IAB. I just erased this formula, but if you remember, after reducing to common denominator, we received negative IAB and negative IAB. So we add them together, there will be negative 2IAB. W conjugate plus A plus IB W conjugate and minus A minus IB W. That's what we get from this term. Yes, we multiply it by W conjugate. W will be gone here. W conjugate will be gone here. Equals to 0. Now, of course, we are trying to get rid of this coefficient before completing the square. So let's divide by this coefficient the whole equation. We'll have W conjugate minus, because of this minus, A plus IB divided by 2IAB. Yes, this minus, by which divide I brought here, minus A minus IB divided by negative 2IAB, and this I forgot, of course, W conjugate here, and W here equals to 0. Now I want to consider this coefficient staying with W conjugate and W. This number, I will denote it for convenience K, just to give it some name. A plus IB divided by 2IAB equals, let's divide A over 2IAB, will be 1 over 2IB, and plus IB and IB will cancel here, 1 over 2A equals. Now, for convenience, I will multiply the numerator and denominator in this fraction by I, by negative I. Then I multiplied by negative 1 will be 1, and here will be negative I. So I will write 1 over 2A minus 1 over 2B I. Because here we multiplied and divided by negative I. Right? So it is negative I, we hit here negative I, and 2B multiplied by I negative 1, which is 1. So this is number K. Let's see the other coefficient. What is the other coefficient? A minus IB divided by negative 2IAB equals negative 1 over 2IB, and plus IB and IB is gone, 1 over 2A. And again I multiply and divide by negative I, numerator and denominator, and negative I with this negative will be positive I in the numerator, and I times negative I will be 1. So it will be 1 over 2A plus 1 over 2B I. So this thing is nothing else. If this is K, then this is K conjugate. Right? So I can now rewrite my equation, this equation, underline it sometimes so I will not forget what we're dealing with. And this is also important, K. That's a K. So I will not forget what we're dealing with. And I will rewrite this equation. W conjugate minus KW conjugate minus K conjugate W equals to 0. Now we can complete the square. I will factor out W conjugate, W minus K, and as usual we are left with negative K conjugate, and here instead of W I will write W minus K plus K equals to 0, so nothing has changed. Now I will have W conjugate W minus K W minus K, and minus K conjugate minus K conjugate equals to 0. Now I think I will erase a little bit more here to have room to write. I think everything that is written well, or I can just write here. Don't really need this part anymore. Don't really need this part. So I will factor out W minus K. So I will have W minus K. When I factor it out, what I'm left with? W conjugate minus K conjugate. Yeah, this is K conjugate. Yeah, I forgot to call it conjugate. W conjugate minus K conjugate, and this term K conjugate I will take to the right hand side. K conjugate. So what's left here? Modulus of W minus K squared equals modulus of K squared, or W minus K modulus equals modulus K. So this equation, this will be equation 2 for today. This equation tells us what will be the image of this straight line. It will be a circle of radius K with a center at point K. Yes? A circle of radius K modulus centered at the point, let's call it Z0 equals to K. Certainly, if you substitute W equal to 0 in this equation, if W is equal to 0, you have received negative K modulus equals K modulus, which is true, of course. So W equals to 0 is on the circle. So this circle does pass through the origin. You can make an approximate picture of this circle. For instance, in my picture, both A and B are positive, which is not necessarily, we did not make this assumption when deriving the equation, but for illustration, since A is positive, yes, K, this is expression for K, I will rewrite it again here, K equals 1 over 2A minus 1 over 2BI. That is K, right? So where is K? Suppose A is greater than 1, then 1 over 2A will be less than 1, will be some small number, I don't know. Here, for instance, yes? 1 over 2A. And 1 over 2B, because B is a little bit lesser than A in my picture, so 1 over 2B will be a little bit greater than 1 over 2A, and it has negative sign before. So it will be somewhere here, for instance, yes? Negative 1 over 2BI. And then, what happens next? we can draw this circle. The center of this circle will be here. This is the point K, right? And the circle passes through the origin, of course, because this distance is exactly modulus K. So it will go somehow approximately like this. This circle doesn't look very beautiful. You can make it better. You can make it look better. So there is this arc going like this. I would say this is a rather decent circle. That's the image of the line. And you can try to perform a similar exercise. For instance, take a line passing through points 2 and I. That's line, yes. Or take some other line and see the image the circle you will obtain. Out of curiosity, you can take one of the coordinates negative. For instance, take a line like this, passing through -1 and I. Also a good exercise, and derive it. But we derive it in general case. What is interesting here? What is interesting? Every note, it must be one-to-one transformation and onto, so every point on the circle is the image of some point of the line. For instance, I can guess that since this is the real number, I believe this point must get into this point as a result of transformation. And for any point on the line, you can find its image for this point, and now I have a good question. The origin must be the pre-image. The origin must be the image of some point on the line under the transformation. So that's an interesting question. What is the pre-image of the origin? Our transformation W equals 1 over Z. So W equals to 0 is the image of what point in the line? That's an interesting question, and we will answer this question probably not in this lecture, maybe in the next one, or in one of the nearest, next one or the one after that. And so we're almost done with inversions. The only thing I have to do as well is to prove an important property of inversion, conformality of inversion. What is conformality? Conformality is the preservation of angles. Conformality is the preservation of angles. Yes, we discussed it already for other transformation, and now we would like to discuss the conformality of inversion. 1 over Z. Conformality of inversions. Conformality of inversions. So we will have to consider, we will prove that the angle between two curves or two straight lines in a particular case is preserved under this transformation, under an inversion. So let's start with drawing a picture. Yes? Geometry class, we must draw a lot of pictures. Let's draw a picture of some situation. So for instance, we have two curves intersecting. We have two curves intersecting, and we select some points that lie close to the point of intersection. We call this point of intersection Z, for instance, and we will draw a line, and there will be points close to point Z. Why close? Because we want to find an angle between the tangents to the curves at these points, and it will be almost the angle between secants, and as a limit, in the limit will be angle between these secants. So this will be point Q, this will be point P. That's our names for these points, and they lie, it's without reducing generality, we can assume they lie on the same ray emanating from the origin at angle phi, and as a result of inversion, of course, this ray will transform into the ray, into this uniform angle. Yes, you're interested in this angle. In this angle, we count angles counterclockwise. I will call it alpha. The first angle we will call alpha. This is the angle between them. And as a result of an inversion, this ray will go into ray negative at angle negative phi, right? And there will be which Z lies will go into some ray here, right? And it will be something like this, and this will be angle we will call beta. So this will be Z prime, the image of Z. This will be P prime, the image of P. This will be Q prime, the image of Q. Our picture is approximately accurate, yes, because I see, for instance, that Q was closer to the origin than P. Now, after inversion, it will be farther away from the origin, yes, because the modulus will be the reciprocal. I think it's a really decent picture. We will also denote the angle, this angle, which is the argument of Z, will denote theta. So this angle respectively will be negative theta. I think it's a good picture. We perform transformation W equal 1 over Z, and before considering this problem of proving the conformality, I want to prove a little lemma, an auxiliary statement. What is this auxiliary statement about? It's very easy. Whenever we have 3 points P, Q, and Z in the complex plane, angle between them, angle P, Z, Q, will be argument of Q minus Z over P minus Z. That's our lemma. let's see, I will make a picture here. Suppose we have 3 points. Right? Suppose this is P, this is Q, and this is Z, right? And the angle between them, angle PZQ. I will denote it theta for convenience. This will be theta. I will translate the whole picture to the origin. So point Z is mapped to the origin. Just translation of the whole this triangle, right? So point P will arrive somewhere here, and point Q will arrive somewhere here, and the argument of P, suppose some angle alpha, and the argument of Q supposes some angle beta, and this angle theta is the difference between them. I will denote them by difference. This beta I will make more visible, so it's clear that it doesn't end here, it goes all the way to Q. So this number is not Q anymore, it's now Q minus Z, right? And this is P minus Z. So you know the rules of multiplying and dividing complex numbers. If I say that Q minus Z equals modulus Q minus Z e to the power I beta, and P minus Z is modulus P minus Z e to the power I alpha, I divide this by this. So I will have Q minus Z over P minus Z equals modulus Q minus Z over modulus P minus Z e to the power I beta over e to the power I alpha, or I will continue writing here, it is equal modulus Q minus Z over modulus P minus Z, it doesn't matter for some positive number, e to the power I beta minus alpha. So, and beta minus alpha is exactly theta. So indeed, angle theta is the argument of this number, right? Angle theta is the argument of Q minus Z over P minus Z. That's what we are going to prove in this lemma. I will write the result of lemma here, so it will be always with us. Angle P Z Q equals argument of Q minus Z over P minus Z, and I will leave it in frame, and I will erase anything else that does not need it, that is not needed anymore. So we have proved this lemma. It was actually an exercise in one of the previous chapters. This lemma was included as an exercise. Problem number something in the material following chapter 2. So now let's see our current situation. This lemma will help us to calculate what we need. Let's look at this current situation. We have these numbers P, Z and Q. And according to the lemma we have proved alpha is, according to this lemma, alpha will be the argument of Q minus Z over P minus Z, our original angle, right? Where, now let's consider our points Q equals R e to the power I phi, right? P equals R small, some modulus. The modulus of Q is R capital, the modulus of Q is R small, e to the power I phi. Z is rho e to the power I theta. Rho is the modulus of Z apparently, right? And as a result of inversion, this point going to Q prime equals what? What happens as a result of inversion? 1 over Q, yeah? So it will be 1 over R e to the power negative I phi. P prime equals 1 over R small e to the power negative I phi. And Z prime is equal 1 over rho e to the power negative I theta. So these 3 points, as a result of inversion, move into these 3 points in inversion, right? And angle alpha becomes angle beta. Beta will be the argument, according to our lemma, of Q prime minus Z prime over P prime minus Z prime. And we need to show that alpha is the same angle, beta is equal to alpha, right? We need to prove that beta is equal to alpha. And what we are going to do when considering this proof, I will, if I have some number psi, not z, not p, not just some number, complete number psi, I can write it as modulus psi multiplied by cosine of its argument. Suppose it is alpha plus I sine alpha. Or it will be modulus psi cosine alpha plus I modulus psi sine alpha. Right? This is the real part of psi, and this is the imaginary part of psi. Real part of psi, this is imaginary part of psi. So when I divide imaginary part by the real part of psi, imaginary part psi over the real part psi, I will receive tangent alpha. So what we are going to prove, that tangent beta will be the same as tangent alpha. So we will calculate our number. This is our number. Alpha is argument of this number. So we will calculate this number and find the ratio of imaginary part to the real. It will be our tangent of angle alpha. And then we will do the same for this number. It will be tangent of beta. Yes? So we will start with calculating the number Q minus Z over P minus Z. And then we will find from here tangent alpha. This will be the beginning of our calculation. We will do it